Hi there. So today we're going to talk about properties of exponents, and we're going to do it in the context of circles and circle dilations. So, so here we go. This blue dot is the center of this board in terms of its equal distance from here to the top of the whiteboard and from the bottom, and equal distance from here to this side of the whiteboard and to that side. So it's kind of in the center. Well, it is in the center. So we're going to make circles, and we're going to dilate them and see how fast we can make this thing grow. So let's start with a nice number of nice measurement for, all right, I'm looking for my straight edge. Shark fins. I'll be right back. All right, here we go. This is what I was looking for. So we'll start with a nice, easy measurement. We'll do, you know what? We'll do 5 centimeters. Here's the center, 5 centimeters. And this 5 centimeters is going to be the radius of our circle. So any number you see here is going to be in terms of centimeters. So we're going to go ahead and do this. So a circle is just the collection of points equidistant from another point. So here's that center point, that little dot there is the center of the board, 5 centimeters. There we go. All right, so there we go. So we have one circle with 5 centimeter radius. Now we're going to double that, and we'll see how big this thing gets. So doubling it, which means it's going to be 10 centimeters. So that's going to put us to right here. There we go. So we've doubled it. Now we're going to double that. So from here, the center, to this point out here, that's 10 centimeters. So we're going to double that, so that shall be 20, which puts us to right here. There we go. Let me just double check that that's visible. It's hard. It's a little lighter, but you can see it down here. So here's our circle. This is doubled the radius. This is doubled the double. Let's keep this train rolling. Let's see. So we're going to double that. So that was 20, so we should get to 40. So that's going to put us out here. Man, look at that. So 40 centimeters is, well, there we go. My mark. So 40 centimeters is what we want. And this string is my protractor. This is keeping the fixed distance from the center to the new circumference, which is 40 centimeters away. All right, there we go. So there's doubled, double the double, double the double, the double. I think I might have lost track of my doubles, but we'll just keep this train rolling. Then we'll come back to that in a second. All right, now we're going to double that. So it was 40 centimeters. So I keep putting the cap on the pen. Why? 40 centimeters. Double that to 80. And then we're going to run out of room here. I can already tell we're going to run out of room. There we go. So there we have some concentric circles. And by the way, these are called concentric circles because they all have the same center, concentric. The center point is that blue dot right here. So this was our initial radius of 5 centimeters. We doubled that, doubled the double, doubled that again, and then doubled this again. So look at that. Wow. So within 1, 2, 3, 4 doubles, we've already gone beyond our board. And if we double again, we wouldn't even see it. Because doubling 80 centimeters would put us at 160 centimeters, which a meter is 100. So, I mean, it's off the screen. You can't even see it. That's way over there. So there we go. So we've doubled and doubled and doubled a few times, and now we're out here. So we're going to pause the video and reset the video, and we're going to explore what we just did here. All right, so here we're going to explore these properties of exponents in terms of these concentric circles. And so we have our initial radius of 5, and then it went to, let's see, then it went to 10. I'll keep track of it here. Here's 10. And then that doubled to 20. And then that doubled to 40. And then that doubled to 80. And if we keep doubling, we'd end up off the screen over here somewhere. So we're going to explore these, but let's kind of play around with this. We just did some stuff. Let's play around with what we got. So let's see. The first thing I want to do, let's play with circles and figure out how big these circles are in terms of a number. So we're going to make a little table here on this side. So we have our radius here. And then, so it'll be 5, for example. And then the area, and the area of a circle is pi times the radius squared, like so. So what that means is for this thing, the first one, the area is pi times 5 squared, which equals, let's see, 25 times pi, which we could approximate that to, I wrote it down here, 78.5. And that is centimeters squared, whereas the radius is centimeters. So these are centimeters. The area is centimeters squared. Anytime we're talking area, it's squared because that's how we measure area. If we were to cut this whiteboard up into little tiny squares that measured 1 centimeter by 1 centimeter, this circle, this smallest circle, would take up 78.5 of those small 1 centimeter squares. So let's keep going. 5, then it becomes 10, so pi times 10 squared, which is going to be 100 times pi, which is about 314.1 cm squared. I'm not going to write centimeters squared anymore because I've already said, hey, the area, it's all centimeters squared. And now I'll just go along here, 5, 10, then we get 20. Then we get pi times 20 squared, which is going to give us 400 times pi, which for our purposes today, we're not going to be looking at all the exact, or this is, by the way, this is the exact. We're not going to be looking at the approximate value, but you could just take 400 times 3.14 and get your approximate value. And then we'll go up here to 40, and then we get pi times 40 squared, which is 1600 times pi. And we'll do the other one, 80 pi times 80 squared, which is 6,400 pi. There we go. So there we are. So there's our radius of these given concentric circles and their approximate areas or exact areas in these cases. And but we're looking at properties of exponents. So we're going to look at this. We're going to look at this stuff here. So we're going to look at these. So I'm going to actually erase some stuff. I just did all this great work, but I'm going to erase it. But that's okay. So, but I'm just going to look at this here. Whoop. All right. Let's see if this will work here. Nice. All right, there you go. So I cleaned up the board a little bit. Well, totally cleaned up the board, except for this. This is that same column, but I added on this other column. So this is still the radius in terms of centimeters, 5, 10, 20, 40, 80. And I guess we should throw in the 160 because we didn't quite make it there, but well, we can pretend we did. Number of doublings, though. I added this column. So at 5, we hadn't doubled anything yet. That was 0. But then we doubled once, and we got to 10. And we doubled again to get to 20. And then I might pause right there and kind of break this down. So doublings, what we're saying, what that means is we're going times 2. 5 times 2 to get to here. But we're using exponents, so we need to keep track of that 2 even when we're starting out. So we could say 5 times 2 to the number of doublings, which in this case is 0. And for the 10, that's 5 times 2, but we're looking at exponents, so 5 times 2 to the first. And here, let's see, 20, it's 5 times 2. How many doublings? 2 right here. So it's 5 times 2 squared. So, and then we get to 40. We've gone then to 3 doublings. And so what that means is we have 5, because we started out with 5, times 2. But then how many times did we double that? 3. Because that was the third doubling. 1, 2, 3. And we go again to the 4th doubling. 5 times, let's see, 2 to the 4th. Great. Okay, we're starting to see a pattern here. Once we get to the 5th doubling, which we didn't actually do, but that's kind of the beauty of mathematics. You can just see what it would be, even if you didn't do that. So let's see, 160 would be 5 times 2 to the 5th, because by this point we would have doubled 5 times. All right, so we're going to break down the properties of exponents here. We'll do this in, we'll do turquoise. So then, let's see, this means, well, there's 0 2's multiplied by 5. So it's just, which is one way we can think about anything to the 0. It's just, well, it's multiplication-wise, it'd be just 1. So 5 times 1. And then here would be 5 times 1, 2 multiplied by 5. And then here we'd have 5 times 2 2's multiplied together. And then here, 5 times 2, but we have 3 2's multiplied together. And then 5 times, let's see, this is going to be 4 2's multiplied together. Like so. And as you can see, this is one of the reasons why we use exponents, because by the time we get to the 5th, 6th, 7th, whatever, larger number of doublings, it's going to get really cumbersome to write that many 2's. Because this means 5 2's multiplied together, and then times 5. So let's say, let's play around with this a little bit. Let's say we did, let's say we had 20, but then we're going to see what happens if we double that by some other number of doublings. Let's say we did 20 times, let's just make one up. We'll do 4. We'll do 4 more doublings. So 20 times 4 doublings would be this. So let's break this down a little bit. But first let's break down the 20. This is, let's see, the 20 is 5 times 2 squared. And then 20 excuse me, 2 to the 4th. Well, that's 2 to the 4th. So let's see, how many 2's do we have multiplied all together? Well, we have 2 here, and then 4 here. So all together, I'm going to write this out, and you're going to see why we use exponents, because this is just going to get so cumbersome. Well, 5 times 2 times 2 times 2 times 2 times 2, 4 2's, and then 2 2. Okay, great. So then what this means is we have 5 times 1, 2, 3, 4, 5, 6 2's. So let's take the big picture out. Let's just look at what's happening. If you have some exponent, some power, let's say 2 to any power, 2 to n for any power, times 2 to some m power, 2 to the mth power, what that means is we're going to have 2 to the, let's see, what do we do to the 2 to the 4? 2 and 4, we added them, so 6. So this is n plus m. So this is one of these properties of exponents. And your base doesn't have to be 2. It could be anything. So generally, to generalize this, I have class in a few moments. Generalizing. I think I might have one too many L's. Generalizing. If you have any base, we'll call it b, to the nth power times b to the mth power, that means you're going to have b to the n plus m. So this is a general rule for, this is called the product rule of exponents. If you're multiplying powers, you add the exponents. But the powers have to be the same. Or the bases have to be the same, excuse me. So here's some properties of exponents. We looked at it in terms of circles, and we found some interesting stuff about exponents too. Bye. There's actually, before I say bye, there's actually another one that's called the quotient rule. This is called the product rule because we're multiplying. Product rule of exponents. We'll do another one. It's called the quotient rule, which means we're going to be dividing. But we'll start with multiplying. Bye, everybody.